Okay, APChem kids, this is a video on how to calculate the pH of a weak acid solution, which is not as easy as calculating the pH of a strong acid solution. And that is mainly because weak acids do not completely dissociate, and they exist in an equilibrium position. So since they exist in an equilibrium position, what we have to use are our rice tables. So looking at a strategy for how to calculate the pH of the weak acid solution, one thing that I do want to point out here before we get too far, and I'm going to go here in red, is that when I say we're looking for pH, you should always kind of consider that also means you're trying to get to the hydrogen, that's trying to be a hydrogen ion concentration. Okay, so you're trying to calculate the hydrogen ion concentration when you're asked to calculate the pH. You're trying to get to that H plus, or as you know, H3O plus hydronium ion, same thing, just with the water attached on. The other thing about weak acids that you should have picked up by now is that there is a list of what we call Ka values. Ka values will not be anything that you need to memorize. You will get a table of them, or they will be embedded in the question. AP Board doesn't expect you to memorize the Ka values, but know that they're only accurate within 5%, and that's going to be very helpful for us with this strategy of calculating the pH for weak acids, because in a lot of cases it means that we can simplify and make an assumption, which will be very good to do. So here is a list of steps. When we're thinking about a weak acid, the first thing you're going to want to do is to list the major species. So think about what is in solution. Choose the species that is going to produce the most hydrogen ion concentration, and you write the balanced equations for them. It might be one species, it might have two species. And then you have to decide which equilibrium will dominate. Now, these three steps right here, although it seems cumbersome, as your book will tell you, it really does pay off when we get into more complex problems. So I'm starting out this lecture with kind of giving you this information to kind of always look at these steps, and this is the steps that you should use to calculate weak acids. Then you're going to want to write the Ka expression for what we call the dominant reaction, the reaction that will give the most hydrogen ions. And then you're going to list the initial concentrations and calculate a rice table just like you would. And then this is new stuff as well, solving for X the easy way. And I'm going to kind of like point that out while we're doing our first weak acid rice table kind of work, okay? But first, what I want to do before we do a full-out blown rice table problem with a weak acid, what I do want to talk about is this ideas of choosing the species that produce the H plus and write the balanced equations for them. So looking at this problem here you've got a 0.08 molar aqueous solution of a weak acid. We're calling it HCN, and notice they're giving you the Ka, and notice that Ka, not very large. And that's one thing with a list of Ka tables, you should start being able to look and decide which one is within the weak acids would dissociate more hydrogen ions than others. So make sure you're kind of looking at that. The fact that that is a -10, I'm inclined to think that the dissociation is not happening as much as if it was, say, a times 10 to a -5. Then that dissociation would be happening a little bit more. Okay, so now imagine this HCN in a beaker, and it says that it's an aqueous solution. So as we have written here, see it says it's an aqueous solution. So think to yourself, what are the major species in solution? Give you a minute to think about that. Oops. Do you have down HCN and H2O? Those are the major species in solution. Why is an H plus or CN minus a major species in solution? Well, the reason is because that is a very weak acid and there is not very much dissociation going on. So you have to keep that in mind when we're working with these acid-base problems. Now, when it says to write the equations, and I should have, but I don't, I should have these in double arrow here. So let's see if I can get them on with that's my best attempt to double arrows. Here I'm writing the two equations, HCN plus H2O. Okay, there's going to be this dissociation value. And whenever I write the equation, I always write the Ka next to it. Notice that 6.2 times 10 to the negative 10th. That's the Ka for HCN. And then water, the dissociation for water, as we know, is a Kw, which is really a special Ka. Some books even still call it a Ka. 1.0 times 10 to the negative 14. So now, between these two reactions, I like to use this kind of wording here. Who's going to control the pH? Who is producing the most hydrogen ions, or hydronium ions in this case? Would it be the HCN, or would it be the water? And hopefully you are recognizing that the answer to this is indeed, the water. Or the HCN, sorry, that should be the HCN. And the reason why it's the HCN is because that Ka value is larger by order of 4 magnitude than the dissociation of water. Okay, moving on. All right, here is an example problem that we have. Let's say that we're given HOCl, hypochlorous acid, and I gave you the Ka value. Calculate the pH of a 0.1 molar HOCl. Okay, so the first thing, actually, that we're going to do is I'm going to hit pause. Okay, so the first thing that we're going to do is we are going to list the major species. And the major species on this is HOCl and water. Again, it's a weak acid, so there's not a lot of H and not a lot of OCl going on in order to dissociate. Then it says to choose the species that can produce the H+. And what I mean by that will produce the most H+, and write the balanced equation for them. Well, in this case, you could go through and say, okay, HOCl, here's my double arrow, that's going to make H plus OCl minus, and that's what that Ka value is right there. And then you could say H2O, double arrow, H plus OH minus, and that would have a Kw of 1.0 times 10 to the negative 14th. That should be a negative 14. Oh, I'm struggling. Negative 14, that's a 1.0 times 10 to the negative 14th. And clearly you can see that the HOCl will dominate. So now what I'm going to do is I'm going to write the Ka expression for that. And I know that the Ka is equal to 3.5 times 10 to the negative 8, and that is going to equal the concentration of H plus times the concentration of OCl minus all over the concentration of HOCl. Now I'm going to write my rice tables, okay? So with my rice table here, and I'm going to just go and add another page on here because I'm running out of space, so we're just going to add another page, and I'm just going to write from here. So with my rice table, the equation that's dominating, that's producing the most hydrogen ion, would be HOCl going to H plus OCl minus. And initially, we were told we have 0.10 molar. These are zeros. So there's my I, here's my C, here's my E. There's going to be a consumption of that HOCl, and we're going to allow for the dissociation to happen. This becomes the change equation. So these are pluses here. Okay? So now substituting that back into my Ka equation, I will get this. I'm going to pause for a minute, do a little bit of work here just to save some time on the video. Okay, so what I did is I took this equilibrium line, just right here. I took the equilibrium line and I substituted that into the Ka expression. So notice that it's x over 0.10 minus x. Now remember I told you that there was an easier way to kind of deal with that 5% rule. And here's the deal, is that amount of dissociation of that weak acid is so small compared to that 0.1 of that initial concentration that we can assume that it is negligible, the amount of dissociation of that x. So we can simplify it to this term right here, x squared over 0.1. And that saves us from having to do the quadratic equation. More importantly, that saves us time on the AP test, which is an important thing. So x in this case turns out to be 5.9 times 10 to the negative 5. And what we can do, just to prove that it is okay, is that we can see if our approximation is valid by taking 5.9 times 10 to the negative 5, dividing it by the initial concentration, which was 0.10, and then multiplying times 100. And indeed, we would end up being, that is the amount of H that is dissociated in this equation. And that's not with it, that's with definitely well below the 5% of the Ka values. So it's a good approximation. We're good to go. This is a great shortcut to take, okay, and to think about it. It really does work. You don't always have to use the quadratic equation. Now remember, if you look back at the earlier problem here, what they wanted us to do was to calculate the pH. So what we're going to do here is we're going to then say that pH is equal to the negative log of the hydrogen ion concentration, which ends up being 5.9 times 10 to the negative 5th. And that gives me a value of 4. Let's see, how many sig figs do we have here? I believe it's 2, so 4.23. And there you go. You just calculated, or I showed you how to calculate the pH of a weak acid. Now in your textbook, and I strongly suggest that you go through and you look at this one. It's on page 655, it's example 14.1. What if you have a mixture of weak acids? And AP Board would like to do this to you. I've seen this on the AP exam. The thing to think about, though, is that they're not all that mean to you because what they will give you is a mixture with very different Ka values. And if you will notice here, which I'm going to, that would be the Ka value that you have to use. The other ones are so much smaller, you can consider them to be negligible, and you won't have to worry about it. So really the dominant reaction is that of the HNO2. You don't have to worry about the HCN. You don't have to worry about the water. So that makes it a very simple way to solve the problems of a weak acid mixture. And if you're asked to calculate the pH. So definitely for sure, check that out in your textbook, page 655, and I believe it is example 14.9. That's it for this lesson. Hope you have a good day.